Hi everyone, in this video as part of STEManuary, I'm going to be discussing diffraction gratings. Diffraction is an effect whereby waves can bend or spread out when they pass through a gap or past an obstacle that's around the same size as the wavelength of the wave you're considering. All of my discussions are based around diffraction of light waves. However, you can also consider diffraction for other types of waves, so for example, water waves or sound waves. In one of my previous videos, I was discussing single slit and double slit diffraction. That's to say the diffracted intensity you get when you pass light through either a single slit or two very narrow slits, and this is the Young's double slit setup. When viewing the diffraction pattern on a distant screen, you can see intensity maxima, so bright spots, but also minima, so dark fringes. A diffraction grating, occurs when you actually have lots of very narrow slits very close together, so many slits, often 100 slits per millimeter or something of that order. So this means the diffracted light you're viewing is coming from a large number of slits with each contribution interfering on your observation screen. And this gives rise to very sharp, bright intensity maxima, and also then in turn dark minima, so gaps in your fringes. And in this video, I'm going to be discussing the main formula you can use to work out the spacing of the intensity maxima, or these bright fringes, as a function of the wavelength and the spacing between your slits. This is something you've already studied. Now is a great time to pause so you can write down everything you can remember and check it off as we go through the video. But otherwise, I'm going to get started on the whiteboard. So let's start by considering our Young's double slit setup. So here we have many slits very close together. This is not going to be as good a diagram as I would hope. There we go. Oh. And the spacing between the slits is given by D. So I'll try to mark this on my diagram here. So this is the spacing. So now let's assume that we're, so this is going to be my normal direction. So we've got coming in, again, plain monochromatic light, so a single wavelength. Lambda. And as I said in the introduction, with diffraction gratings, because each light from each of the slits is going to interfere on your observation screen, then we get very narrow, bright intensity maxima on my observation screen. And we call these maxima of different orders. So if I consider the forward direction here, at theta is equal to 0, so I'm going to measure the angle relative to the normal. This is my 0 order maxima. And then at some angle theta, call this theta 1, then I'll get my first order maxima. And in between these, we just get dark patch or fringes, so there's no intensity. So this is my first order maximum, sorry. I should use my plurals correctly. And there will also be a first order below. So again, this is theta 1, and then there'll be the n is equal to 2, so the second order maximum up here. and this will have some angle, I'll call that theta 2. So in order to calculate the points or the angles at which these maxima are detected, there's an equation that you need to remember, and that is that d sine theta is equal to n lambda. So d is the spacing. Theta here is the angle from the normal. N is the order of the maximum. So 0 is n is 0. Then the first is n is 1. And I drew out n is 2 up there. And lambda is the wavelength. And actually, you can explain this equation by considering the difference in the distance that light has to travel from two adjacent slits. So if I try to draw this bigger down here, then if I consider a particular angle, so theta, to the observation point, and this should be a right angle. So let's consider the n is equal to 1 case. The slit above, light going from that has to travel an extra wavelength in distance. So the path difference is 1 wavelength. So that means these two rays still interfere constructively. But yeah, each slit has a relative path difference of 1 wavelength relative to the ones above and below. And of course, when you go to the second order maximum, then this path difference becomes 2. And if you want to check this by trigonometry, we've got d here. And this is my angle theta. So sine theta is equal to lambda over d, or d sine theta is equal to lambda. So this equation allows me to work out the angles to the diffracted maxima as a function of the wavelength and the spacing, but often what we're measuring when we view these diffraction patterns is actually the fringe spacing as a function of distance. So again, if I had, let's just consider again some diffraction grating here, and I were viewing it, so this is little d, and then if I'm viewing it at an observation point d away, then we can use trigonometry to work out, say, let's say this is, call it theta 1, so this is my n is equal to 1 maxima. So, and I want to find out this distance here, so the spacing x. So using trigonometry, tan theta 1 is equal to x over d. However, we're viewing this diffraction pattern suitably far away that we can use something called the small angle approximation. So that's that tan theta is approximately equal to sine theta, which is approximately equal to theta in radians, that is, for small theta. So this means that x over d is approximately equal to sine theta 1. And we can then use our formula, so sine theta 1 is going to be n lambda over little d. So we can then rearrange to get that the spacing between the fringes as a function of distance is going to be, well, so the spacing, or the delta x, is going to be lambda times little d over d. And the position of each point, so I could call it xn, is going to be n lambda d over d. There are a couple of final things I'd like to note before we finish this video. Firstly, because we know that sine theta, so the which is related to the diffracted angle, must always be less than 1. So when theta gets to pi over 2, then sine theta will be 1. So that actually limits the number of orders that you can see in your diffraction pattern. Another thing to note is that the spacing in as a function of angle between your fringes depends on the wavelength. So if the wavelength's shorter, then the diffracted peaks get closer together as a function of angle, and in turn using this equation on the right hand side as a function of position. This means that if you illuminate a diffraction grating using white light, which is made of a number of different wavelength components, you'll still get a white peak in the center, because that's where all colors have their 0th order maximum. But then after that, your later peaks will be, you'll see each of the individual colors, because they'll each have their diffracted maxima at different points. And specifically because in the electromagnetic spectrum, violet and blue have the shorter wavelengths, and then red is the longest. As you go out as a function of angle, the first one you'll see in each order is the violet, and then the red will be the outermost one. So I hope this video has been useful. I hope you've enjoyed either learning or revising some material about diffraction gratings. If any of you have any questions, feel free to email me, and otherwise I hope to see you all soon.